Ramachandran plot. We'll do a very rudimentary programming. We'll not try to understand everything, because then it would be a failure, because it would be too much for you. But I will give you a test of programming, that's all. So don't be worried, and try to, you know, try to have the fun part. It is very interesting. Programming is interesting because programming is interactive. You know, if you tell it something, it will give you some return. It's like a boxing bag. It will give you some return. So with that, we will go to a directory for the Ramachandran plot. Give me a second. Programming, and this is RP Pros. Yes, here. Okay. So last day we actually covered fair bit of Ramachandran plot, and we also told you about, we also discussed the theory a little bit, the theory and the historical perspectives also about how Ramachandran came up with this plot and why it is such a big invention in the field of proteins. We tried to give you some idea. So in the Ramachandran plot, again now we are from sequence, we are going to structure analysis, and this is the last module for this course. So we try to be very attentive. It's very interesting, but you have to focus. So from N starts a protein sequence, then you have C alpha, then you have C, then again you have N C alpha C. So N C alpha C, N C alpha C. That's how a protein chain progresses. And this C is the carbonyl carbon. That is the carbonyl carbon. This this C alpha is connected to the side chain. So R1, R2, R3, etc., etc., etc. So now, if you look at it carefully, this is an triatomic unit in the along the main chain, along the central trajectory of this protein, that is being repeated in a cyclic permutation. So N C alpha C, then again N C alpha C. So 1 2 3 1 2 3 1 2 3 1 2 3. That is the rhythm. N C alpha C, N C alpha C, N C alpha C, N C alpha C. That's how it is repeating. So after 3, again it will come to 1. So that is a cyclic permutation. So that means that if you have two bonds connected to each other, you will have two atoms connected to each other, you will have a bond, you will have a bond, and it will have a bond length. Then if you have 3, this is also something we discussed, two atoms, that is one bond, that only can have one geometrical parameter, that is the bond length. Then 3 atoms, it has two bond lengths, BL1 and BL2, and you will have a bond angle, BA12, right? And then if you again add one more atom, then this 4th atom can actually go out of plane. 3 atoms define a plane. The 4th atom can remain in the plane, or it can go out of plane also. So that gives rise to another kind of angle, which is the dihydral angle or the torsion angle. So in a 4 atomic entity, you have 3 bond lengths, BL1, BL2, BL3, 2 bond angles, BA12 and BA13, BA23, and then you have something that we call torsion angle. So that will obviously, it will be around that central bond. So that bond connected by 2, 3. Because 1, 2, 3 will be part of one plane, and 2, 3, 4 will be part of another plane. I want to determine the angle between these two planes. I showed you this example also. This is 1, 2, 3 and 4. So 1, 2, 3, that defines this plane. 2, 3, 4 defines this plane, and that is the angle. So now using this fundamental conception, if we look at the protein backbone or protein main chain, then we already know that there is a cyclic permutation of 3. It's a 1, 2, 3 rhythm. So that means 3 bond lengths, N C alpha, C alpha C, and Cn. C alpha C and Cn. These 3 bond lengths are repeating. So it will have a value here, it will have a value I'm using this as a marker. Then again NC alpha is here, then again NC alpha is here, like that. Then this bond C alpha C, it is here, it is here, it is here, and like that. Then this, the third one, let's use a cross, it's here, here, and again CN here, so it will be here. So CN is the peptide bond, by the way. You have to recognize and acknowledge the fact this is the peptide bond. So it has a partial double bond character because carbon is connected to two equivalently negative electronegative atoms, carbon and oxygen and nitrogen. So both will pull electrons from the carbon catalyte, positive charge cloud, and therefore there will be a continuous delocalization of electron cloud, and that will render the partial double bond character with a trans conformation that we also discussed in the last class. The omega angle about this always has 180 degree close to, that is trans, and this has a bond length of 1.42 angstrom, or sometimes actually so it is between the single carbon, this is actually 1.35 to 1.42. This is the range of this bond length. So that is between the single bond length, which is 1.54 angstrom, for carbon-carbon, and close to that for carbon-nitrogen, and the carbon-nitrogen or carbon-carbon double bond length. So it is between. So that means it has a partial double bond character, not complete. So now we are getting this 3 bond lengths in repetition. Now let's take a look at the bond angles. NC alpha C is the first bond angle. NC alpha C is the first bond angle. Then NC alpha C, then C alpha CN, C alpha CN, that's the second bond angle. This one and this one. Then the third will be CNC alpha, CNC alpha. So again you will find NC alpha C, this one, NC alpha C here, and again NC alpha C here. Then you find C alpha CN, let's say this is a dollar sign. So C alpha CN is here, and C alpha CN is here. So again this is repeating, since the 3 atoms are repeating. So all the bond angles are also repeating in a cyclic permutation of 3 entities. Then you have 3 torsion angles, and you remember I mentioned about phi, psi and omega. So which one is about which? It looks a bit clumsy, so I'll rub off these. So the phi angle, remember, psi phonetically resembles with C. So from there you try to remember. So both these are about the C alpha atom. So C alpha C is psi, and C alpha N, whichever is left, is phi. So that's how I used to remember at least. So C alpha C, so this bond is psi angle. So that means it is N C alpha C N. So these 4 atoms will define these phi angles. N C alpha C will have one plane, and C alpha CN will have another plane, and the angle between these two, the dihydral angle, that is the psi angle. Similarly, about C alpha N, this bond angle is phi, and about Cn, this bond angle is omega, which we already told. This has a mean value or expectation value of 180 degree, which means trans, which means like this, the 2 bulky groups are farthest away from each other. So this will become cis if this will be like that, they are on the same side, so the distance will be smaller, so it will have more steric clash. This will have less steric clash or steric hindrance. So trans is preferable. And we also discussed that this constitutes a Ramachandran plane. Did we? আমরা কি Ramachandran plane বলে কোনো কথা বলেছিলাম আগের দিন? বলেছিলাম?
Ramachandran Plot বলার সময় স্যার আপনি Ramachandran Planeটার কথা বলছেন।
বলেছিলাম 6টা অ্যাটম থাকে সেখানে, না সেটা বোধহয় বলিনি। So since this CN, that's the peptide bond which has a partial double bond character, that's why we are using cis trans. তোমরা যারা chemistry, if you just recall your chemistry, so cis trans is only applicable if there is a double bond. isn't it? তাই তো মনে আছে তো fatty acid bound.
Yes, sir.
So here we do not have a double bond, but we have a partial double bond. That's why cis trans is applicable here. So Cn এর দুদিকে দুটো C alpha, তাহলে এদিকে থাকবে একটা অক্সিজেন, এদিকে থাকবে একটা হাইড্রোজেন. So this constitutes a plane. Why? Because আমি যদি তিনটে অ্যাটম ধরি, these three atoms, they will be on the same plane because three atoms define a plane. Now by virtue of having this torsion angle omega fixed at 180 degree, obviously plus minus something, সবসময় 180 হয় না, একটু 19-20 হয়. So then this fourth point is also falling on that same plane because two angles will fall on that same plane. One will be 0 degree, মানে যদি জিনিসটা এরকম হয়, cis, মানে এটা কি are you being able to visualize it properly? মানে আমি বলতে চাইছি যে এই যে প্লেনটা, এই প্লেনটা আবার ঘুরে গিয়ে একই জায়গায় একই প্লেনে পড়বে কখন? When will it fall in the same plane? Two ways, either this or this. These are the two options. ঠিক কি না, তাই তো? So this is your trans, this is your cis. Sorry. So if this happens, then that is equivalent to this trans, you know, farther away. Then this angle will be 180 degree. এটা কিন্তু dihydral angle. And if this happens, that is close to this. So this will be 0 degree. কি বোঝা যাচ্ছে? বোঝা গেল?
Yes, sir.
Fine. So cis we only find for proline, we are not going to do that. So this is called the Ramachandran plane. Oxygen and hydrogen, they are also geometrically fixed in a way that they also fall in the same plane. So all these 6 atoms fall in the same plane. Now from here, this C alpha is also connected to another such plane which completes a two plane entity. We can draw it here also. C alpha, let's say C alpha like that. So C, so then it will be connected to N, C alpha N, NC, NCC alpha, NCC alpha N, yeah, okay, N, and then this is connected to C, this is connected to C, and then this is again connected to another C alpha, this is O, this is H. So আমি এটা ভালো আঁকতে পারলাম না, but you just imagine all these are on the same plane. So that is two Ramachandran planes, and that we call a Ramachandran dipeptide unit. So we can Google it quickly, have a better visual. So this is the Ramachandran dipeptide unit. See, this plane is about this CN bond, this plane is about this CN bond. The C alpha is connected to N and C at both ends. So this C alpha will have both phi and psi. This is the phi angle, this is the psi angle. So effectively this, you know, tells us the rotation of two planes on top of each other. না অন টপ অফ ইচ আদার না, টু প্লেনস, মানে আমি ভাবতে পারি এই দুটো প্লেনের মধ্যে কীরকম রোটেশন, কীরকম ডাইহাইড্রাল রয়েছে, সেভাবে আমরা এটাকে ভাবতে পারি. সো দ্যাট দিস ইজ কল্ড দি রামাচন্দ্রন ডাইপেপটাইড ইউনিট. ফাইন, ওকে, ফাইন. সো নাও উই উইল compute all these main chain geometrical parameters. These are also called internal coordinates, by the way. They are also called internal coordinates. এটা মাথায় রাখতে হবে এই কথাটা, because they do not have any frame dependence, they can be computed internally. মানে আমি যদি এই অবজেক্টটাকে এখানে রাখি বা এখানে রাখি বা যেখানেই রাখি, এই অবজেক্টের ইন্টারনাল অরিয়েন্টেশনটা একই থাকবে, মানে এর রেসপেক্টে এটা কতটা নেমে আছে, all these internal parameters. So the surface description, the thickness, the volume, the area, all these are internal descriptors. And if you are talking about bond length, bond angle and torsion angle, they are called the internal coordinates. So we will not really go into detail of programming back because that will really take a toll, but there is a program that I will offer you, I will provide you with. This is written in a language called Fortran. Fortran is an ancient language, but it's a very effective language even today for very high level number crunching, very fast number crunching. This is how a Fortran program looks like. Fortran, the word literally means format transformation, and nuclear physics, biophysics, astrophysics, these are the streams that uses it frequently even today. Several molecular dynamics packages have been developed in it. I am not going into programming details, that will take another several classes, I believe, but just to say a little bit, these are called commenting out, just general description. So this part of the code which is here commented out by this exclamation signs, they are not for the programming language or the compiler that is going to compile this into a machine language. Mane eta to this is written in ASCII text. That means you have English and English character and English alphanumeric, and you have numbers, and you have some syntax. So this will be compiled into a binary, and you will do this compilation, that will be a binary 10 machine language file, which will be the executable file. Not directly this can be executed. And this is the default of programming languages, not of scripting languages. C, Fortran, we have to compile them. So this part is for the user. This part is written for the user and for the programmer, the developer, whoever is opening this file. This part will not be read by that compiler, and so it will be skipped. So if you want to skip a line within your code, you want to make it for people to read only and not for the programming language, you just start in Fortran with this exclamation. So say, what is this doing? This program calculates all backbone internal coordinates of a given polypeptide chain from its 3-dimensional atomic structure. Internal coordinates here refer to bond lengths, bond angles, and torsion angles. And what are these bond lengths, bond angle, and torsion angles? We just described NC alpha C, AC alpha C, Cn, and phi psi omega, and the bond angles accordingly. This part of the code is called declaration. You are defining here what you require to execute and run this program. What are the variables? What are the variable types? You can have 3 variable types in Fortran. Character variable, that means your string names, amino acid codes, chain ID, all these are string variables. And before that, we have to look at how a PDB file looks like. This is a PDB file. It has a lot of header lines, how the crystal structure was done, in which date, what was the source, what are the experimental details, what is the space group, all these things, and then it will start from start giving up the coordinates. So this means atom, whatever is starting with the string atom, has a coordinate, so of one atom, and one heavy atom, and hydrogen atoms does not come in crystal structure unless and until it's ultra high resolution structures, which are very rarely found, less than 1 angstrom resolution. This is the amino acid 3-letter abbreviation, so that's a glutamate. This is the residue number 22, and this is the nitrogen, and then this is XYZ. So if you have to locate this in space, in obviously in its own unit, is in angstrom, of course. So these are the coordinates XYZ. So from the coordinates, we are displaying the PDB file in rasmol, pymol, things like that, and this we actually will read in our program and calculate the values of the bond lengths, bond angles, and torsion angles. So to calculate the bond length, what do we need? How do we calculate the bond length? We have 2 points here and here. So this is x1, y1, z1. This is x2, y2, z2. Let's say this is C alpha and this is N, and they are connected. Okay. So the distance, the bond length, will be square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. Understood? বোঝা যাচ্ছে তো? দুটো স্পেস, দুটো পয়েন্ট আছে 3D তে, তাদের ডিসটেন্স হচ্ছে আমার এইভাবে ক্যালকুলেট করি, কার্টেসিয়ান। ক্লিয়ার তো? আশা করি। আচ্ছা, so similarly if you want to calculate bond angle, এইটা একটু বোঝা হয়তো, কিন্তু আমি যেটা বলছি, you go through vectors, you have to understand what are vectors. So if you have these three bonds connected consecutively, we want to calculate this bond angle. So let's say this is v1, this is a vector, and this is v2, this is another vector, but the direction is like this, in the same direction, v2 and then v1. So then you have to take the dot product of these two vectors, v1 dot v2. So these vectors and the dot product is v1 mod v2 mod cos theta, and that theta is the angle. So theta will be cos inverse v1 dot v2, this is vector notation, divided by v1 mod and v2 mod, মানে the magnitude দিয়ে ভাগ করতে হবে। Did you have any chapters of vectors somewhere? Are you familiar with this dot product and cross product? Maybe in your higher secondary, isn't it?
Sir, in 12, yes, sir.
Never you had.
Yes, sir, in class 12.
We did some in class 12, higher secondary exam.
Okay, so yeah, so that's how it is. I'm not going into further details because v1, okay, nothing, it's very simple. v1 is x1 you can say it's x1 I cap plus y1 j cap plus z1 k cap. Similarly v2 will be x2 I cap plus y2 j cap plus z2 k cap. So that means now if you want to do v1 dot v2, so that will be x1 x2, only these terms would remain that have the same unit vectors, because cos 0 is 1 and cos 90 is 0. So if you take I cap dot j cap or j cap dot k cap or k cap dot I cap, that will obviously involve a cos 90 term which is 0, so those terms will be vanished, those will be cancelled out. Only the terms that has the same unit vector, this is called unit vector, those will remain, and those three terms will be x1 x2, I cap dot I cap will be 1 into cos 0, that is 1, so that is 1. So x1 x2 plus y1 y2 plus z1 z2. So this is the numerator, this part, v1 dot v2 is this, and then v1 mod is similarly root over x1 square plus y1 square plus z1 square. Similarly v2 mod will be root over x2 square plus y2 square plus z2 square. So now you have all the terms, you just take this ratio and do the cos inverse and you get back the theta. So that's how bond angles are calculated. For torsion angles, again a bit more complex, so I will not really explicitly derive up to this xyz level, but I will say in terms of vectors. So this is a torsion angle, let's say 1 2 3 4 1 2 3 4. So this is v1, this is v2, this is v2, and this is v3. So you want to have the angle computed between these two planes, isn't it? So for these two plane, for this plane, let's imagine this first. So you have a hypothetical line, an imaginary line joining this, just to render that that's a plane. So v1 and this is v2. So now if I take a cross product, which is a vector product, v1 cross v2, that will give me the normal to the plane, normal of the plane, but normal to the plane, the vector that is normal to the plane and passing through this point of intersection. That is the definition of cross product. So v1 cross v2, let's call it n1. So that is the normal to this plane. And then now imagine this, the second plane separately. I mean, etaki alada kore aঁকছি আবার, like that. So that will be v2 and then this will be v3, and etake ami hypothetically join korlam. So that's one plane, this is another plane. So here also v2 cross v3, similarly v2 cross v3 will give me n2, which is the normal to this plane passing through the point of intersection of these two vectors. So now you have to realize a very key concept in geometry, that if you want to have this angle calculated, that is equivalent to calculating the angle subtended by the two normals. So a plane in 3D, in Cartesian three-dimensional geometrical systems, is defined as its normal. একটা প্লেনকে তার নর্মাল দিয়ে চেনা যায়, ঠিক আছে? একটা বৃত্তকে, একটা সার্কেলকে যেমন তার সেন্টার আর রেডিয়াস দিয়ে চেনা যায়, একটা প্লেনকে তার নর্মাল দিয়ে চেনা যায়. সো a plane is defined by the normal. Similarly, this plane is defined by its own normal. So these normals will interact somewhere, intersect somewhere. That angle is equivalent to or related to the actual dihydral angle. Maybe they are related by a relation of 180 degree minus theta, but for as a standard practice we call them, we treat them equivalently. So it actually ekhane chilo. So now we take V2 cross V3, so we get N1 somewhere and N2 somewhere. This is N1 and this is N2. সবসময় মাথায় রাখতে হবে কোনো দুটো ভেক্টরের ডট মাঝের অ্যাঙ্গেল ক্যালকুলেট করতে গেলে তাদের ডট প্রোডাক্ট নিতে হবে, আর তার কোনো দুটো ভেক্টরের ক্রস প্রোডাক্ট নিলে সেটা মিন করবে ওই দুটো ভেক্টর যে প্লেনে আছে সেই প্লেনের নর্মাল এবং পাসিং থ্রু the point of intersection of those two vectors. That is the definition. So now we have N1 and N2. We can take N1 dot N2 and that will give us the angle in the similar way to the bond angles. So that's the definition. So tinte line N1 is equals to V1 cross V2, N2 is equal to V2 cross V3 and N1 dot N2. তাহলে প্রথম দুটো ক্রস প্রোডাক্ট, পরেরটা ডট প্রোডাক্ট, অ্যান্ড তার আবার তাহলে এটাকে আবার একইভাবে N1 mod N2 mod দিয়ে যদি আমি ভাগ করি এবং তার যদি cos ইনভার্স নিই, দ্যাট উইল বি মাই টরশন অ্যাঙ্গেল. লেটস সে এটাকে নাম দিলাম টাউ. সো দ্যাট ইজ দ্য থিওরি. এর থেকে বেশি ডিটেলস আর যাচ্ছি না, তাহলে চোখ হয়ে যাবে সব. So we will not discuss it how we are doing it exactly, but just to say that we are taking this, see that we are reading these atomic the lines that are starting with the atom tag, and then we are storing these variables line by line. ফাইলটাকে রিড করা হচ্ছে এবং ভ্যারিয়েবলগুলোকে স্টোর করা হচ্ছে. কাদেরকে যদি n হয়, c আলফা হয় এবং c হয়, যে কোনো একটা হয়, অন্য কোনো অ্যাটমকে কিন্তু আমরা স্টোর করছি না. we are only interested in the main chain atoms, and then in using this theory we are calculating the bond lengths, bond angles and torsion angles. I will not go through any other pieces of the code because it will be tangential probably, কারণ অনেকটা হয়ে যাচ্ছে. So I'll try to brief it. So I'll run this program first of all. So this is i-Fort called Intel Fortran in detail. That's the Fortran compiler, recommended Fortran, and Fortran has different versions. The first version came in 1977, that's why it is called Fortran 77. Then the next update came in 1990 and 1995, so they are named accordingly, Fortran 90 and Fortran 95. i-Fort is a 90 compiler, Fortran 90 compiler. Using 90 is recommended, not lesser version, but 90-95 are almost similar, so doesn't make much change. Another thing, the earlier commands developed by earlier versions of these languages are subset of the new packages, so you are not missing out. You still on any previous command, so you still will be able to run your Fortran 77 code using a Fortran 90 compiler, because they are not ruled out. The earlier commands are not ruled out, but new commands have been created and joined even for the same operation. So i-Fort, and then I'll try to use the same line, so I'll increase the length here. Then the name of the source code, so that ends with a .f extension. এই এক্সটেনশনটা খুব জরুরি. যদি পার্ল প্রোগ্রামিং হয় .pl হবে, যদি C প্রোগ্রামিং হয় .c হবে, যদি C++ হয় তাহলে .cpp হবে, যদি ম্যাটল্যাব হয় .m হবে, ইত্যাদি প্রভৃতি. যদি পাইথন হয় .py হবে. So for Fortran .f, and then this -o, that means we are compiling this to an executable which is a binary, which is a 10 machine language file that will be able to execute. So that name already is there. I will redo it, bb.exe. So executable, since I want to create an executable, I have created a file with the name .exe. So this has now compiled. Now ls minus lart করলে last যেটা তৈরি হয়েছে সেটা হচ্ছে bb.exe. So that's the last file that have been created. Obviously this is created by this. Now there is a command called file, and now if you type this, it will show you, it is saying that bb, it is elf 64-bit lsb executable, etc, etc, a detailed description. And if you want to open and in vi and have a look, it looks like একদম হজবরলা, কিচ্ছু বোঝা যাবে না, because all of these are special characters. They are written in binary language that the machine is able to interpret, not human minds, not like us. Of course there are machine language experts, of course they can able to identify and decode it. So we leave it to that, to the machine. And how this works, .bb.exe, now / means we are running this program now, just like mouse clicking operations, we can run something on the command prompt, and / means it is being run from the current directory. And then we have to specify the input. The input here is the pdb file .2heq.pdb. so that's the syntax. So it has run within seconds, মুহূর্তের মধ্যে রান করে গেছে। ও কিছু আমাকে শুরুতে এটাকে বলে verbose, so it is giving some verbose, so verbally it is communicating, saying this, because I have told it to do that way. It doesn't have any intelligence, আমি যা বলেছি সেই অনুযায়ী লিখেছে। That is not important, the output files are important. Output file in Fortran can be generated in different types. We can specify the file name, and we can also specify the unit name. এই একটা জিনিস একটু ফাইল খুলে দেখানো যেতে পারে, will not be that difficult to grasp, I suppose. So if we type open, see it is saying open unit 1 file fname. So fname is a variable, and this is old, so the what, so আমি এটা হচ্ছে ইনপুট ফাইলটাকে কিভাবে রিড করা হচ্ছে। সো এই কল গেট আউট মানে গেট কমান্ড লাইন আর্গুমেন্ট, আমি ওই জন্য কমান্ড লাইনে আফটার মাই প্রোগ্রাম নেম আই হ্যাড টু ইনপুট দ্য ফাইল নেম, right? So that's how this is getting input, and that's an old file because it was previously existing, it was an input file. If you want to create something, write into something, that would be an output file. Important thing is to note this unit. So now it will read from this unit, means it will read from this file, and if we do not specify the output file name, then it will write to some file with the name fort dot. So fort.23 for instance, in this case whatever is written here, this is the unit name. This file has not been opened previously, so it will in situ or on that spot it will open the file called fort.23. If this is 76, it will open fort.76 and write into that file. So that's the idea. So now these three, as you can see, are the output files with three different unit numbers, and everything starts with fort dot something. So the main output file for this program, since I know I have written this, is fort.25. The other two are accessory, we might choose to skip as well. See here, this is the output. The first, this is res id, that's the residue identity, so that is the residue number and that is the residue type. If you had multiple chains, you could have also added a chain id column. Then this is the phi angle, and torsion angles by definition is defined between -180 to +180, where -180 and +180 merges into a same point, just like the international date line, or the in Bengali antarjatik tarikh rekha. So because it merges to the same line, so -180 means going in the anti-clockwise direction, and +180 means going in the clockwise direction, and they are merging into the same point for ±180 degree. So that's the definition. So can anyone tell me why this 999.999 is written here for the first residue in case of phi, and for the last residue in case of psi? কেউ বলতে পারবে এটা কেন? Because they do not fall within -180 to +180, so they are not really a valid number. Any idea কেন এটা আউটপুট দিয়েছে? Okay, because n terminus residue will not have a phi angle. by definition. It starts from N, then C alpha, N C alpha, that's the first bond, while for the phi angle, the angle is defined on NC alpha, so it cannot have the phi angle by definition. Similarly, the last residue, that's the C terminus residue, that cannot have a psi angle because it is ending at CO minus. So C alpha C is the last bond, so it cannot have a bond, a torsion angle defined on that C alpha C, because it's a terminal bond. I hope that makes sense. So these are called dummy variables. So all the internal residues after the N terminus and before the C terminus, all the other residues will have a phi and a psi, and so they will have a phi psi ordered pair just like XY, and they could be plotted in the Ramachandran plot. This is the omega bond, omega torsion angle, and as you can see, I told you several times that this merges to 180 degree, which is plus minus 180 degree again, depending on from where are you coming, from the anti-clockwise or clockwise direction. So essentially this is trans, so close to 180 degree plus minus. And then we have the bond length C alpha C, a carbon-carbon single bond length, which is 1.54 angstrom. So you can see the values are close to that. Then you have Cn, that's the peptide bond. I was telling you 1.35, 1.3332. This is the range. Then NC alpha, it has a little bit of less because of here you have N rather than C. So just little bit less than carbon-carbon single bond length. So 1.546, 1.4647. These are the values. And then you have the three bond angles. One is NC alpha C. This we call the tau angle. This is a very important angle in terms of Ramachandran. So depending on the tau angle, Ramachandran plots actually joins, the discrete regions are joined. I'll show you that in a while. Then you have the C alpha Cn bond angle, which is about 117, and then Cn C alpha bond angle, which is a bit wider, bit more obtuse. So let's first look at the Ramachandran plot with tau angle radiation. Okay, so this is the plot. Okay, so the tau angle, as you can see from here, this has a mean value of 110 degrees, close to 110 degrees, sometime 5 degree less, sometime 5 degree more, and depending on whether it is constrained or relaxed, the beta sheet region and the right-handed alpha helical region in the Ramachandran plot, they are brought close to each other, so that these two different islands, they are now connected in the Ramachandran plot. এটা কেন হচ্ছে, তার কারণ হচ্ছে এটা এই অ্যাঙ্গেলটা এমন একটা জায়গায় রয়েছে, এমন একটা জায়গায় রয়েছে যার সেটা যদি একটু বেড়ে যায় তখন ওটা হেলিক্সের দিকে, তখন হেলিক্স আর বিটা শিট খুব ক্লোজলি চলে আসবে, it will influence the nearby phi and psi angles. So Ramachandran plotted ideal values এর কথা বলেছিলাম আগের দিন. So beta sheets have an ideal value of 180 degree minus 180 degree, which is this point. So that is absolutely flat. কেন 180 degree flat, trans একই প্লেনে থাকবে. So flat beta sheet, বিছানার চাদর যেরকম হয়. আর হেলিক্স বলেছিলাম minus 48 minus 58 for left handed and plus 48 plus 58 for right handed. So আমরা যদি এরকম torsion angle কখনো ফিট করতে যাই, we will get a helical trajectory if we use those values. So minus 48 minus 58 বা minus 50 minus 60 এরকম রিজিয়নে যদি এই অ্যাঙ্গেলগুলোকে ফিক্স করতে যাই, we will get a helical trajectory. So this tau angle is situated in such a place that its deviation will bring these two regions close together. That means there would be patches, there would be sequences, there would be structures, for local structures which will be between beta sheets and alpha helices. It will not be so clear whether it will have both propensity, both trends. মানে একটা শঙ্করের মতো, মানে একটা ইটস লাইক আ হাইব্রিড, সেটা না দেবায়ও না ধর্মায়, ঠিক যেন হেলিক্সও নয়, ঠিক যেন বিটা শিটও নয়, সামথিং ইন বিটুইন। সো that's the significance of the tau angle. Especially this is very important for beta sheet geometry, which is a difficult geometry to handle for protein folding. So now we have run the program and we have the desired output. Now the next task will be to see these points plotted in the Ramachandran plot, and for that we have copied this into this RP progs folder, where we have we'll use MATLAB for this plotting. সো এই যে আউটপুটটা, এই যে 4.25, এই 4.25 এরই আর একটা ভার্সন আমরা এখানে কপি করে নিয়েছি। সো দিস ইজ ডিভয়েড অফ দি আননেসেসারি কলামস, ইট অনলি হ্যাজ দি residue number, residue identity, and the chain identity, and the phi psi omega. And also note that the N terminus and the C terminus residues are truncated because they do not have both the values. They either have phi or psi. So we have considered in this subset only those residues which have both the phi and psi angle defined according to the definition. So MATLAB takes a bit to open, we have to be a bit patient. We'll just show you how to draw the how to plot the Ramachandran, how to plot these points in the Ramachandran plot. And this is also a program that once I wrote and it was of much use later on for both teaching and research. This is likewise the Fortran programs have an extension .f. MATLAB programs has an extension of .m, which is no wonder. So I believe this is the program. I will check. So in MATLAB you have a command window, and you can use this edit command to open this and see. Yeah, I hope this is. Yeah, Rama.m, sorry, I'm sorry. So Rama.m is the name of the program. Okay, so this accepts the file as a function, and we have to mention it. So that, see, this is the example, this is the usage, and just try to analogize that. Likewise we showed comments in the Fortran program, commented out by exclamation signs. In MATLAB these are commented by the percentage sign. So whatever you write after the percentage will not be read by the compiler. It is a note for the user and the programmer and the developer. So again, I'm not going into the details, I'm just running the program. Oh no, this is not the program, sorry. Sorry about that. I think this will run. So I'll try this one. Let's see if this is there are a lot of versions, so sometimes I get confused which one, but I hope this is the one. So that's how to use the MATLAB program. That was the usage, that was the okay. I'm sorry, I think I'm not using the right program. So yeah, I think this is the original program. So orig here stands for original, nothing else. So see the program name at the beginning, and then within bracket you name the file name. That's how to use MATLAB functions. So it's just like y equals to fx. You could have returned some y here also. This is like writing f and within bracket x. I hope that makes sense. So now this is the Ramachandran plot. So this is the beta sheet region, this is the right-handed helix, this is the left-handed helix, is the 310 helix, other regions. And as I said, Ramachandran made his plot when there was no crystal structures available in the public domain. So literally this was a plot actually. So obviously when more and more crystal structures became available, people worked on the Ramachandran plot, and it got modified and it got extended. So this is an extended version of the Ramachandran plot that I have used here. This plot is used by a very popular protein structure validation tool called ProCheck. So I believe you can understand that the contours are matching here. বোঝা যাচ্ছে? পাশাপাশি দেখে কি বোঝা যাচ্ছে? Okay, probably আগের কথা থেকে. Yeah. So if you can see closely, I have used these contours here. See these contours. So that is a version of Ramachandran plot used by a structure validation tool called ProCheck, and this was developed by Janet Thornton, and I again had some good privilege to get in touch with her. She's like a mother of structural bioinformatics. She has done, almost she has contributed to every field of structural bioinformatics. So see, this is the plot that I have used here. So these points that fall in within this red zone, they are called the allowed regions of the Ramachandran plot, and then whatever is within that blue zone, they are combinedly called partially allowed or generously allowed, and there would be some points falling outside the Ramachandran allowed regions. These regions, they are called disallowed. So there would be some points which will always be disordered or disallowed according to Ramachandran plot. They will provide the entropy, because you have to realize that the protein is always moving, it's not a static object. For our analytical purposes, we freeze it into an inanimate object, and then we so it's a solve the coordinates by crystallography. So crystallography is operated on an inanimate object, inanimate crystal, a frozen crystal. That's not the living form of the protein. In the living form, as I showed previously, it is really fast and moving always. So there will be some points which will not be ordered and falling in the disallowed regions of the Ramachandran plot in all proteins almost, and they will provide the entropy, the breathing space. But if you get lots of points on these regions, so then you doubt that probably there is something wrong with the structure, and you want to go back to correct them in your experimental data. It's a common practice for crystallographers. But again, let me mention, intrinsically disordered proteins, which are intrinsically disordered, they do not form a compact fold unlike globular proteins. They have more flexible appearance in the Ramachandran plot in terms of the Ramachandran plot constraints. So you will probably get much more points here, because these generally form the disordered loops and turns and bends and things like that. So with that I would like to complete, and I hope you gained some idea about bioinformatics, both in terms of sequence and structures. What was to the extent possible, I tried to in limited time, 4 hours in total. So